So, we will continue with this module on printed wiring board technologies, which also encompasses high density interconnect process issues, because as I have mentioned time and again, for advanced packages to be mounted on, let us say, an organic substrate or a ceramic substrate, you need to understand the IOs, and if there are going to be large number of IOs and if they are going to be mounted on an organic substrate, then the substrate has to be compatible with the package and the package design that you have envisaged. Therefore, you are now trying to understand the technologies that enable us to build a substrate that is compatible, that can sustain, that can provide electrical performance, and also sustain the reliability issues that we are talking about. Therefore, it should have good thermomechanical reliability. So, thermomechanical reliability is not just applicable to the chip level packaging, it is also very much applicable to board level packaging issues. In the last class, we have been discussing the interconnect hole formation methods. So, we will continue with that. We have seen, if you recollect, the various methods to drill a via or a microvia. It can be a mechanical drill. The mechanical drill limitations we have seen. If you recollect, the limitations today in terms of the equipment is something like 150 microns, but there are a few equipments in the market today which can drill 0.125 mm, which is 125 microns, but they can be expensive. And it is not only that, if you use those kind of mechanical drills, the next issue to consider is that how well you can wet the barrel, whole barrel, and the inside of the dielectric hole to make it conductive. So, your chemistries and the technologies needed to plate the through hole, or it can be a blind via, or it can be a buried via. Nevertheless, as the size decreases, and if you are going to depend on a larger aspect ratio, then you will have difficulties in electroless plating. Therefore, the alternate methods like the photovia technology, which uses a very thin dielectric, and you are trying to use only that thin layer, typically about 15 to 35 microns of the dielectric material, which needs to be opened up by photolithography methods, which we have seen earlier, and the via has to be electroless plated and further electroplated to create a microvia structure. Here the aspect ratio is comfortable to work with, and therefore, you have much better yield in a photovia. But further to that, we have seen over the last 7 to 8 years that the laser drilling has picked up very fast. The equipments have been affordable. Companies have invested in the capital of the company to have laser machines to improve the yield and the throughput. In the laser drilling method, you have two types. One is the carbon dioxide laser, and the other is the chemical laser, which is basically YAG, yttrium aluminum garnet. You have modifications of YAG also, like the neodymium doped yttrium aluminum garnet. As you can see here at the bottom, you see the structure of the garnet material, and this is also the atomic arrangement in the crystal of a garnet. Therefore, on the one hand, you have the photovia, which is a very good option. There are two options in the laser which have been practiced for large volume production. One is the carbon dioxide laser, and the other one is a YAG laser. The only thing is, photovia is lowest in terms of cost due to parallel processing, which means you have a mask, you have a substrate that is well prepared, you have a photoresist material that is applied onto the surface, and then using simple UV lithography, you can transfer the image on the entire panel. So, compared to a mechanical drill, or in some ways a comparison to the laser drilling, the Photovia, because of its parallel processing, is economical, but we are looking at in terms of hole reliability and the dimensions of the hole that you can generate using a Photovia as compared to a laser drill. Carbon dioxide laser will drill fairly fast. It has a good drill rate. Any dielectric can be drilled. So, you have flexibility here to choose various types of substrates and thinner dielectrics in the sequential build-up layers to create microvias. But using carbon dioxide laser, you cannot open copper, because if you look at buried vias where include copper, then the carbon dioxide laser will not be able to drill on the copper layers. Therefore, you need to switch during that time to chemical or YAG. So, YAG laser, yttrium, aluminum, garnet, you can drill copper with it. You can drill small holes, fairly small holes, and any dielectric can be drilled. Typically, we have seen today in the industry and even in the research papers and prototyping activities in this SBU methodology, that laser drilling has gone even up to 50 microns. Therefore, during the last 7 to 8 years, we have seen extensive development in the use of new dielectric materials and the compatible nature of laser drilling with those dielectric materials. Then we have plasma drilling. It is a very cost effective parallel process similar to the Photovia process. It has got high yield. Environmentally, it is very clean, because you have a special chamber for it where you create the plasma, and almost any dielectric material can be processed. Therefore, cost wise, if you compare plasma with Photovia, Photovia will be less expensive, but plasma still is not a preferred industrial choice for microvia drilling. Now, what I would like to show here is a sample of a laser drilling process. So, you can see here that there is a substrate, typically an organic substrate, mounted on a laser drilling machine. Now, the data from this for this drilling process is taken from your CAD work. So, it can be a inner layer drilling typically to create microvias, or it can be a top or bottom layer after the sequential build-up process has been completed to create the microvia structures. So, you can see here that typically the copper is drilled, and then you can see the cross section here, the dielectric is opened up, and finally, you end up at the base copper. So, essentially you can do what is known as a depth drilling. So, you can see once again, if you use YAG laser, you can combine both copper as well as dielectric drilling to a definite depth. Now, this kind of depth drilling is required if you want to create blind vias in a structure that you have built up from a core substrate. For example, if you have created a 4-layer core and then you want to build a 2-layer at the top and a 2-layer at the bottom to create a 8-layer sequential built up technology, then these kind of controlled depth drilling to create microvias for your signal lines, interconnects are very useful. Now, we will come to some of the classic examples that we have witnessed in the last 10 years for creating high density interconnects. So, all of you are aware that you have a single sided board, a double sided board and a multi-layer board built by conventional techniques. Now, that really does not give a high density board, a high density organic substrate. Now, in those cases you are typically using for example, an FR4 core, and a similar material is used as the prepreg material for building the inner layers. And finally, your board thickness comes to around 1.6 mm or maximum 3.2 mm. You may have multi layers, but your interconnections is still dependent on the through holes, which are fairly large. So, in order to improve the density on the printed wiring board, and in order to qualify these substrates for advanced packages, IBM introduced this technology called surface laminar circuit. At that time, around the year 1997, 1998, this technology was introduced and termed as SLC, surface laminar circuit. It is a trademark belonging to the IBM organization. So, it is basically a pure organic packaging solution. Now, SLC, what does it contain? It has two major parts. One is an FR4 substrate, the other is the built up layer. So, that is why it came to be known as sequential built up technology or SBU technology. So, you will start with a core. For example, this is a core, let us say a 2-layer core, and then you build an additional layer at the top and additional layer at the bottom to create a 4-layer structure, but built by non-conventional method using thin dielectrics at the top and the bottom and opening microvias and interconnecting these pads and tracks to the inner structure by very small microvias of the order of 4 mils and so on. So, you essentially in this technology you are describing a new method to create an SLC layer. It is also a method to have your printed wiring board or printed circuit board as a MCML structure using existing PCB technologies. So, the advantage of using SLC method in those days when it was introduced was the attractive concept that you do not have to change major of your printed wiring board process line, a couple of changes in terms of imaging and a couple of new materials like the dielectric that you would like to use specifically to get very thin coatings is all that was required to convert or improve the density part of it or high performance qualification of your PCB to what is known as a multi-chip module L type substrate. If you recollect, we have discussed what an MCML is, and typically it is an organic substrate, and you can create an MCML using thin dielectrics. So, the outline of this SLC process is that it uses a photopolymer to build additional layers. That is the first key point here, to build additional layers. That means, you have a normal PWB core that is already available in your design, and essentially you now try to design the additional layers by not using a prepreg, using very thin photopolymer layers. This has to be a very thin layer, so that your aspect ratio is high. At the same time, you can handle them. So, for example, here we are talking about in this particular case a 35 micron thick dielectric material on which you can very comfortably open up a 100 micron via structure, and you can easily plate the 100 micron via to establish connection from the top layer to the immediate adjacent layer. So, the uniqueness of this is that you are not creating larger depths of microvias. The opening is only on the thin dielectric and it connects to the immediate bottom copper plane. Therefore, the reliability is very high. Photo imaging creates blind and buried vias. It eliminates mechanical drilling. So, this is a very important key point that made this process successful. Now, otherwise you have to depend on the limitations or the lowest drill bit that your NC drilling machine can work with, and still depend on cleaning the via that has been mechanically drilled to clear the debris and so on, and make it conducive for electrolysis plating. The buildup can be done on both sides. This is another attractive feature. So, as I said earlier, if you have a core substrate, you can do the buildup on one side or even on the other side. The buildup can be uneven, which means you can have one buildup here and then you can have 2 layers built up on the second side, which means if you start with a 2 layer core, you can end up with a 2, 3, 4, 6 layer structure, but at the same time you can see 5 layer structure, 1 at the top, 2 at the bottom and 2 as the core. So, it is a 5 layer printed wiring board built by SBU technology or built up technology. Unlike in the conventional case, design wise, to avoid warpage and so on, you try to make it a even structure. If you build 2 layers at the top, you also build 2 layers at the bottom. But in this case, this is not necessary, because we are talking about thin structures and you will not see the effect of warpage in these cases. No glass fabric in the polymer. If you compare with the prepreg material, there is a filler material along with the resin. For example, in FR4 you have a glass fabric along with the epoxy resin in the prepreg material. Therefore, it is more rigid. You cannot reduce the thickness. Typically, you can work with 200 microns to start with, and hence because of this the entire structure is light and thin. So, typically even if you build a 6 layer board using SBU technology, you can still end up with a 0.8 mm total thickness of the board, which is an indicator of the high density that you can achieve. You can build 2 to 4 additional layers from your core. So, this is known as sequential build up technology, and there are various methods, various routes that many companies have tried from this original SLC technology. So, I would say that the surface laminar circuit technology was a key driver for this industry to enter into high density interconnect structures, which enabled usage of these printed wiring boards for various handheld products like your digital camera, your camcorder, and then PDAs, all handheld products including the current iPad and the mini computers and so on, have tried to utilize SBU technology in their systems. The features of this SLC technology is that it is high dense. At that point of time during 1998 when it went to production, and it was targeted for 2000, the year 2000, when the product can be gone full fledged into the industry, especially in Japan. 1 mil vias were used, okay, that was the target, and 1 mil line and spacing. So, this is a very great deviation from the conventional multilayer boards that we have been used to. Then SMT pads can be placed on blind photovias on the top surface and the bottom surface. That means you are avoiding additional pad area that needs to be provided for surface mount devices. So, you can use the photovia land itself as a pad. For example, if you have a thin dielectric and if you are opening up a via here and then you are plating this via, then your surface mount device, one of the pads can sit on this microvia. Similarly, if you have another via here, the other pin can sit here and so on. So, this is the package. So, you are gaining a double advantage in the sense that your via becomes secure, which means you can fill this via with a metal paste, or you can plate it additionally to provide rigidity to your microvia, and then also you can mount your component on the via, so that it becomes a via on pad type of structure, and it reduces the board area, increases the density. More design freedom because of usage of microvias, routing capability is very high, and you provide additional layers for fanning out your microvias to inner layers. Ability to accommodate flip chip or a C4 technology and bare die, hence classifies under MCML, used currently in video camcorders and handheld products, telecommunication products, and so on. This is a picture of the original, the first product that came out using IBM's surface laminar circuit. These two were introduced by IBM's Dr. Sukada, working from IBM Yasu in Japan. You can see that in the left there is a PCMCIA card, it is a LAN adapter card, where you can see typical numbers. For example, the thickness of the board is only 0.7 mm, it has got 6 layers. So, 0.7 mm and then having 6 layers is not possible via the conventional multi-layer board methodology, because the prepreg, because the limitations are two. One is the prepreg thickness, the copper foil thickness that you normally get in the market, and third is the mechanical drill via size structures. So, in this particular example, 6 layer board, there is a 4 layer FR4 core that has been taken, and 2 build up layers have been created on one side of a 4 layer board. So, it is typically a design issue. It has been decided to have a 4 layer structure here, and then 2 layers have been built on one side. So, the other side did not have the sequential build up methodology at all. So, these were provided with a lot of Microvia structures to interconnect to the core substrate. And you can see here it has accommodated flip chip, one which is 7.5 mm square, and the other is a flip chip 2 which is 4 by 10.8 mm square. So, these are the flip chip substrates that have been mounted. So, you can see this is a classic example, an introduction from IBM about the usage of bare die directly onto the substrates. There is no packaging, it is a bare die flip chip methodology, and it is a reliable interconnect. In addition, you can see all the components are surface mount, including the resistors and capacitors. Absolutely, it has eliminated mechanical drilling except in the core structure, and then no through hole components have been used. So, this is how the progression has taken place from conventional multi-layer boards, where the limitations have been there for high performance because of the size. Now, we have the Microvia showing us how we can generate by proper design methodologies and understanding manufacturing, you can create a high dense Microvia board. Now, this is actually an assembled printed circuit board containing the Microvias. What you see here is a single chip module BGA component containing a C4 device. So, you can see here this is the C4 flip chip, then you can see this is an organic substrate, and then it has got a BGA interconnect. The solder balls are visible. Now, this is the top side. So, on the other side you will see pertaining to these pads, you will see the matrix of the solder balls. Now, the features of this single chip BGA is that it is a 25 mm square package. This can be mounted onto any printed wiring board, if you provide the right registration LANs. It is 0.8 mm thick only with 6 layers. In this case, it is a 4 layer FR4 that has been started to work with, and then one build up layer on both sides. So, it is 1 4 1. This is the type of arrangement that we see in this particular single chip module for creating a 6 layer substrate. Now, in this particular case of single chip module BGA, as I mentioned in the packages chapter, the job of the substrate or the function of the substrate here is basically to just fan out the IOs through the organic substrate into the BGA balls at the other side of the package. The flip chip size here is almost 8 by 8 square, and the smallest via used here at that time is around 19 microns, which is a very remarkable achievement considering that this was the introduction or the beginning of these kind of concepts. Today, using laser drilling, and by the way, this process used photovia method, but today people are using laser drilling to achieve 60 micron or even 50 micron drills. So, what is this SBU process flow? How does it go about? Now, if you look at this figure on the right and you can look at the explanation on the left, you will be able to understand how a microvia is generated and how you make it conductive. Now, let us look at the top. Here is a substrate which there is copper on top side, there is copper on the bottom also, and this is the dielectric material. This is the starting. Now, you do the surface preparation, as you know, coat the photoresist, the green one here what you see is the photoresist, and then pre-bake it. Then you photo expose, develop using your mask. The mask here should contain the photovia elements. So, you can see here this pertains to the openings where the photovias need to be formed. What is the next? You now create the pattern, right. So, in this particular case you are now doing the etch process, and then you can see here at this point of time the base substrate imaging has been formed. So, this is the circuitry, these areas are the circuitry, right. So, a particular layer imaging process has been completed. All of you are aware of this entire process. We have seen this using video highlights. Now, begins the SBU process technology. If you can carefully look at the bottom 3 figures, apply the photopolymer dielectric here. Now, how do you apply this photopolymer dielectric? You can use typically curtain coating, or you can use spin coating. So, the performance of this process, whether it is spin coating or curtain coating, to achieve a desired thickness. So, here thickness is very crucial, thickness is very important. So, assume you have got about 35 microns. Okay. Now, you take the mask that is required for the microvia, place it on top of the cured dielectric material. Now, this dielectric material can in fact be a better dielectric in terms of dielectric constant compared to your host core substrate. Okay. Now, once this is cured, after the microvias have been opened, it is cured. So, now it becomes very hard. So, this particular layer becomes very hard after curing. Now, you have to metallize this microvia. So, you can see that the hole walls are not conductive. So, you do an electrolysis process, then followed by electroplating process, and then you can see all of these layers have been coated with copper. You can see electrolysis first, followed by a flash electroplating to metallize the whole wall, and in addition you can see the whole wall copper at the bottom touches the copper plane in the adjacent layer. So, this is how a connection has been established between this layer and this layer, and then you have the third layer here. You can build another additional layer as we have seen here, same as above, and then you get the fourth layer. Now, you can repeat this process once again to get 2 additional layers, one at the top and one at the bottom, that will give you a 6 layer board. After this imaging has been after the plating has been done, you can image it according to your circuit design. So, this is a very convenient process where you can inspect the process at every stage, whereas in a multi-layer board, once the inner layers are done and if you have combined them in a press, it is very difficult if you have a registration problem or if you have a plating problem in the large mechanically drilled through hole, then you cannot repair the board at all. You have to discard the board. But here at every stage you can inspect, you can rework on the layer and build the additional layers. So, it is an excellent process which was used in the SLC method. People in the industry have modified these processes by using various dielectrics and currently made it compatible with the laser drilling process. So, this is the SBU process. So, as a result of this SBU process, what kind of structures can you get? Suppose you want an 8-layer board and then you have a core layer. For example, you can see here in this particular figure, this is an 8-layer board has been described. The build-up layer is here, another build-up layer is here, and this build-up layer contains the microvias. Right? Whereas here these are through hole structures done by mechanical drilling. This is a PTH, plated through hole. Therefore, this is the core. So, typically this is the core, 6-layer core, and then 2 build-up layers have been done on this core structure to give you an 8-layer board. So, ideally you would place your ground planes in the core layer, and typically in the built-up layer you will have all the signal lines, thin structures. So, ideally you do not want to have too much copper on the built-up layers. So, you will have thin structures, typically 4 to 8 mils in width, spacings are also typically 4 to 8 mils, and then those layers top and bottom will be used for accommodating or mounting your surface mount devices or advanced packages like your BGA, flip chip, CSP and so on. So, the next one is a 12-layer board. You can see here the top one is the built up layer, which means 2 layers have been built at the bottom, 2 layers have been built at the top. So, 4 layers for this structure have been done by built up technology. You can see this is the microvia, and these are the this is a buried microvia. Similarly, here you have the microvias. You can have various microvias in this particular layer interconnecting or connecting to your inner layers. So, this is a plated through hole structure done by mechanical drill, and this is how you build the or increase the density of your board from a simple 8-layer core. Lot of packaging has been done in these 4 layers. So, that is the key to it. So, you can inspect once this layer is completed and this layer is completed, and again if you want to rework, you can remove the dielectric and redo the imaging process. So, that is the advantage of using a build up technology, and this is the cross section of the same process. You can see inner layers containing through hole, buried through hole structures, and the top layer containing the microvia structures. This is the cross section. Now, we will look at a review or a summary of the highlights of the key properties of these materials. The materials in consideration here are the photoliquid imaging system, photo dry film imaging system, laser drilling in conjunction with the resin coated copper foil, and then you have the laser and then the plasma drilling. Now, if you look at the various parameters, so you have these materials in consideration today. If you look at the dielectric cost, the photofilm dry film is very difficult to be made available today. The availability is low, cost is also very high, whereas a liquid is easy to work with. you can work with various coating methods like your meniscus coating or your curtain coating or the spin coating method. Now, the resin coated copper foil that is readily available and compatible with the laser drilling, the cost is fairly high. And then plasma, because it is also fairly a parallel process, but again depending on the thickness of the material that needs to be etched, it can be time consuming. Therefore, manufacturing wise it is a costly process. Now, for medium numbers, industry also prefers to use a liquid photopolymer. If certain industries are still believing or making sure that their feature sizes are easy to work with using liquid photopolymers. But where there is more stringent regulations in terms of tolerances and lower feature sizes that are required by certain customers, then people have to prefer laser drilling. Now, we have a look at the via sizes that are possible. Typically liquid photopolymer you can work from 50 microns. Current day technologies for laser also targets 50 microns, but very safe is 75 to 100. So, typically the range from 50 to 100 should be possible for various methodologies listed here to create a microvia. And as I said, by definition a microvia is one which falls in the range of less than 125 microns, around that number, because otherwise it can be done by a mechanical drill and does not classify as a microvia. The line width and spacing typically 75 to 100 microns for all these processes. Then you have the via diameter in production is currently about 100 to 125, in some cases even more, 150 microns or so that the high reliability is maintained, whereas for prototyping one can go for these kind of numbers. The via layers maximum is 4 additional layers, but in some cases people have gone in for 6 layers. So, typically if you start with a 4 layer board, you can build 2 to 3 additional layers. Dielectric thickness varies from 40 microns to 60 microns, and in some cases it has gone even up to 100 microns to 250 microns. Dielectric thickness control, which is a very key parameter for the technicians to maintain and then understand the working of the equipment. With the liquids it is going to be very difficult, but if you get readily available substrates like your resin coated copper foil along with the dielectric material, because there are some companies which have provided standard thicknesses of dielectric coated with the copper. So, in those cases thickness control is not an issue, it is only the drilling depth that is an issue. Dielectric constant from around 3.5 to 3.8. Now, the key to your electrical performance when you use an SPU methodology is to experiment with new dielectric materials that have low dielectric constants, and that is probably available as a liquid that can be coated using curtain coating. So, the key here is try out new dielectric materials with lower dielectric constants. Glass transition temperature of your core substrate can vary from 125 C or 130 C to about 190 today, that can be used. So, we are also worried about the glass transition temperature of your dielectric material. In some cases you may use a dielectric material with some filler content in that, but in most cases it will be a filler free dielectric material that you will use for the inner layers. Process issues are working in a clean room, therefore, things like a pinhole, debris sitting on the liquid photopolymer with no protection and so on can be very destructive in terms of the yield part of it, because of lot of rejects. Because the size of the via itself we are talking about 75 to 100 micron. Therefore, your pinholes represent a significant defect. And you have to look at the conformability of your drilling process, especially the laser, with the dielectric material. And also, if you are talking about the process issues in terms of the PWB processing, because it goes through the various chemicals, and then the substrate compatibility. In some cases, you may want to use a via filling, as I said, because you want to mount an SMD component on top of the via. Therefore, what type of filling you will do for the microvia filling, and the shape of the via in the case of a plasma seems to be well in tune with the desired results, whereas in the case of laser we could end up with a plateau like this, whereas in a plasma you might get an almost cylindrical shape. So, how do these vias behave during thermal cycling and during the life of the product are some of the key issues that designers as well as manufacturers will be interested in. The other key process issue that all of us have to be aware of is the addition. What is the addition we are talking about? We are talking about a dielectric material that is coated and on which a via is formed. So, we are talking about the plating of the via, and there is the dielectric material here. We are talking about the addition at the surface of the dielectric to the copper. Now, if there is delamination of copper from the adhesive from the dielectric material, then your microvia has failed. So, the key to getting high yield and sustaining during the thermal cycling the natural life of the product is that these microvias should be defect free during its operation, and the plating that happens and the electrolyzed copper to dielectric addition is also a very key issue. And if you are doing laser drilling, again because it is an ablative process, you have to make sure that you clean the hole walls fairly well, just like in your conventional MLB process before your electrolysis plating. So, thickness control, adhesion and being defect free are some of the key issues that one has to be aware of. Now, here is a list of companies which has been picked from various sources, this information, which have if you look at this is probably the starting point, the SLC surface laminar circuit, which used epoxy liquid from IBM Yasu, and this is a photo via process. And then came up various processes from different companies like Fujitsu, Toshiba, Hitachi, Sheldal. Sheldal came up with a readily available substrate that can be used for laser drilling. So, you did not have to worry about thickness control of the materials, and you can see that lines and spaces like 50 to 37.5 microns have been well defined. Dicostate is another major company that came up with photoimageable dielectric material, which is more information is more confined with the company, because it is a patented process called diconic substrate, where you can see the feature sizes like lines and spacing 100 to 125, via land 75 to 300 microns, and using a plasma compatible dielectric material. So, depending on whether you want to use a photovia or a laser drilling or a plasma process, you can adopt the kind of materials that are available. We are going to talk about one or two of these in this particular chapter, just as a case study, because if we want to describe all of these, it is going to take too much of time. Therefore, as a typical case study or an example, we will describe a couple of these processes, and you can see how from the original SLC methodology, how people have modified this technology, yet maintained the SBU concept and then built high density interconnect structures. The first one that we will describe or look at is the ALIV technology. It is an SBU methodology. ALIV stands for any layer, inner or interstitial via hole, which requires no through hole technology at all. So, again just as the SLC, this is a encouraging concept which says you do not have to have a mechanically drilled hole at all in your 4 layer or 6 layer or 8 layer structure. Okay. So, these technologies are not for building a 60 layer board like you normally do in a ceramic board or a, let us say, a 24 layer board in an organic substrate. These are for substrates that are typically used for handheld products, not generally used for your desktop computing motherboard. Okay. So, there you still depend on the existing technologies because it is reliable and well documented. Now, these are for, as I said, simple computing boards which uses DSP processing, which is requiring, let us say, a SIP package or a CSP package or a BGA package or an FPGA module, let us say, which is being used, and so on, fairly small size boards which can be built entirely using a SBU method. Now, why does this technology require no through hole? This is because any 2 layers are electrically connected by interstitial via holes. That means, you can place the vias wherever you want in your design. Okay. So, it requires your ingenuity in the CAD system to fan out your IOs from the packages very comfortably using small microvia structures to remove the heat. You can use them as thermal pads or thermal vias to dissipate the heat from your packages and still maintain the reliability of your system. The IVH in this particular case can be placed in any position. That is the beauty of this process, and the wiring capability is improved greatly because you have more space for wiring. Your wiring diameter or the interconnect track widths are very small, matching with the thickness of the via structures. Typically, you want to use, let us say, if you use a 4 mil via, you want to use a 4 mil spacing as a general guideline. You still can increase the spacing if you are worried about the crosstalk and other parasitics involved with your electrical interconnections. So, on the left, what you see here is a cross section micrograph of any layer inner via hole or interstitial via hole technology. What you can see here is the microvia that has been built up first, it is filled. Then you have the second microvia structure which is again filled, and then you can see another microvia. So, these are basically stacked. This is a stacked microvia structure. Now, there can be questions about the reliability of this stacked microvia structure compared to your through hole structure. So, that is why we say in the case of stacking of a microvia, you do not want to exceed 2 or 3 or 4 layers, because it depends on the conductive paste that you are using to fill the microvia hole structure. The rigidity of the structure is dependent on the properties of the material that you are using to fill the microvia structure, because it should not cave in during your thermal cycling process, and then there should not be too many solvents in the makeup of the conductive paste. There should be no air bubbles or voids, and it should provide very good curing, so that you have very good contact with the adjacent copper structure. So, how do you prepare this kind of board using ALIV? So, use a material called aramid fiber, and the prepreg is made out of the aramid prepreg. So, let us say this is typically about 100 micron or 200 micron. Now, you can use this as a substrate and do a laser drilling based on your CAD data. First, you create the holes. So, you feed it into your laser drilling machine and you get a substrate that has been generated with the microvia structures. Now, using a stencil printing process, because you need to use the right conductive epoxy material instead of epoxy you can use some other material, but the general commercial material, economic friendly material is epoxy resin. So, you mix it with a suitable conductor material. It can be silver, it can be gold, or it can be silver copper or copper alone. It can be finely dispersed, very fine small particles dispersed in this media, and then they can be screen printed or stencil printed into the via structures. You can see here that after the printing process is over, this is by printing. After this process is over, copper foil is taken on top and bottom. So, now you decide what kind of thickness you want. It can be a 100 micron foil that you can put wrinkle free, and treated copper is now placed on top and the bottom, and now this structure is laminated. Okay. So, here what do? You want to cure the material, and you are also using the pre-preg material's physical properties, because it contains some kind of a solvent. It is a B stage resin, as you know, and then you have the uncured conductive paste that has been dispensed in the whole wall. Now, all of these entities together are laminated. Now, you get a very good bonding between the conductive paste, between the pre-preg and the copper at the top and at the bottom, and you get a very rigid laminate structure. So, now this is very suitable for patterning your holes and etching out. So, you can remove the copper here. So, you can create a pattern as you have seen here, and then you can create a microvia again by using your print and by using your photovia methodology. You can open up a microvia, or you can also use a laser drilling additionally to open up the copper and then create a microvia structure. So, layer by layer you can build up. Okay. So, but the essential process is that you get the ready made available pre-preg materials from using aramid. They are of standard thickness, but you utilize and you eliminate mechanical drilling here totally. You can align these microvias like here and stack them to get a comparatively a through hole structure kind of a formation construction, and you can expect if your process is well established, a very good reliability even in these through holes in these stacked microvias. The other one is we have seen briefly, it is called a VI in pad structure, a plated through hole, in this case a microvia by mechanical drilling is filled by epoxy resin and plated by copper to form a lid. So, you can see here these are the lids where a through hole has been plated, and then they have been filled by the conductive material. And if you are talking about very large depth, then the conductive paste material has to flow much better rather than being a thick paste, because you want to cover the entire area of the through hole. Now, VI in pad structure is called because you can utilize the lid of your through hole for mounting your SMD or a BGA, let us say, or a CSP. So, it becomes more dense. You are not required to provide additional pad area on the surface of the board. So, VI in pad structure can save surface area for wiring, enabling the PTH pad to be able to mount surface mount devices. Flow property of conductive epoxy or other resin crucial for minimum shrinkage. Even in the earlier figure, what I wanted to emphasize here is that the material should not undergo shrinkage. So, look at the property of the conductive paste very carefully when you are using for filling the microvia structures. So, resin property is very crucial for minimal shrinkage and electrical contact between layers, because here again you can see this electrically conductive paste is interacting or connecting to your inner layers. So, you cannot lose the reliability in those areas. Minimum PTH diameter is about 150 micron, aspect ratio can be 8 to 10, You can work with this aspect ratio in this process because you are not doing electrolysis plating, you are simply filling it. The aspect ratio in these cases can be an issue if you are using wet process like an electrolysis process, because you need to ensure that your liquid, that is your electrolyte in the electrolysis copper plating bath wets through the micro holes and then provides a very good even thickness of copper. That can be done by micro sectioning, but rather than going through that route, you can work with the filling of the via. Now, what are the advantages of a via in pad? It provides a flat coplanar surface for component attachment. So, you have to do some kind of a polishing at the top. You can see in this particular figure here, if you have provided an extended pad area for the microvia, you can utilize that pad for mounting your BGA devices. You do not have to fill the microvia with conductive paste. So, this is an additional option that you have. So, here you have not utilizing the entire area of the lid of the microvia. In this case, there is no filling, whereas in this option you can place it directly on the lid of the via which has been filled with a conductive paste, but in this case you have to polish the surface at the top and the bottom if required in a different area, and then provide a very good surface, planar coplanar surface for mounting your devices. More traces on PCB escaping devices through the routing channels, because this acts as a, again in this case it acts as a thermal via, and then you can design accordingly that where your thermal via routes can go into the thermal relief planes that you have provided in the inner layers. Increased component density due to absence of periphery vias, potential EMI benefits due to lower inductance, because if you look at the contact point between the BGA solder ball and the pad, it is almost very low interconnection length, therefore, there is low inductance. Thermal dissipation either at the lead joints or under devices by means of heat pipes. So, these structures act as heat pipes, and no via plugging by solder mask required at the component locations. So, otherwise what you do is you plug the area with a solder mask material. So, here you are using a conductive paste to perform that function. Now, we will look at another process as a case study, which is called the B squared IT process. B squared IT is known as buried bump interconnection technology. So, it is a patented trademark process technology owned by Toshiba. B squared IT is a Toshiba technology. The popularity of this is not well known, but Toshiba has experimented with this technology and probably used in a few of its commercial products. So, we will look at this process in the next class in detail. So, what we have seen today is a summary of the high density interconnect processes. We have seen how a SBU process flow is, and we have got into the basic mode of comparing between conventional multilayer boards and high density interconnect boards, and we have seen a couple of high density interconnect processes which have slightly extended compared to the SLC process. So, we will continue with another example called the B squared IT in the next class.